conversion of analog signal to digital signal. The first part of the transmission for digital communication, we began with sampling theorem. Then we are in the middle of quantization. So as I told, there are two varieties of quantization. One is scalar and another is vector quantization. This course is specifically will be dealing or limiting our discussion to a scalar quantization only. Okay. In case of scalar quantization, in a few of initial minutes, I'll dedicate to just refresh whatever you have done, and we can continue where others can join meanwhile. Okay, basically the quantization process is a rounding off process. Okay, so it's basically converts and digital discrete time analog signal, the quantization block, the quantizer in other words. Okay, so this converts discrete time continuous signal or discrete time analog signal to discrete time discrete, or I can say completely digital. Okay, or discrete time discrete in amplitude. Okay, and then we'll use encoding to convert into to code each of those quantized outputs to a binary value, which in turn can be called as a digital signal. Okay, so this basically the quantization process is rounding off process, rounding to the nearest value. Okay, so rounding to the nearest value from a finite set of possible quantization levels. So we took quantization levels to be the number of levels to be capital L, where I'll just make use of different notations in order to be familiar with all different varieties of notations across the resources, so that I will utilize a little different notations for today's session in particular. Okay, number of quantization levels. Okay, we had used a notation of L, which can be denoted in certain resources as capital N, and we had divided the continuous amplitude levels into several sub-regions. Each of those sub-regions is called as a cell. So I can say that region, the region of the discrete region, I can say the discrete okay, I can say in other words regions of divisions, we call it as a cell JK, which I'll be using for this in particular for today's session as R suffix K. Then we took the input message signal as M. I'll be using a notation called as X for this discussion, and the output, basically this was X, this is M, and this we call it as V, and the transfer function that we had called, which converts your continuous analog signal, I'm continuous in amplitude signal to discrete in amplitude signal, we represented as V, which takes a transformation, we call the transfer function as G. Here we denote the V as hex hat. Okay, that's the reason I'm just listing out this for clarity that we proceed in this session. And the function, the transfer function, we had denoted it as G, which I'll be using for today's discussion as Q. Okay, these are the notations that we are going to use to describe further about this quantization process. With this new notations, I can say the number of bits per sample, the number of bits per sample can be the same notation R, which can be now written as log n base 2. Okay, so with quantization levels Bn, where each of those I can say each of the samples, if it represents as m suffix I can vary between 1 to capital N. These are the different levels. Okay, so with that understanding, I will try to proceed to find out, the performance or to evaluate this quantizer. So we have evaluated this quantizer. Okay, evaluation of performance of quantizer. We have already done this. We had already measured the performance in terms of quantization error. Okay, and there is something known as signal to quantization noise ratio at the output. Correct. So these were the two parameters that we had discussed at length, and we had solved, and we have solved already a few numerical problems related to these parameters. Today I'll take a new performance parameter of this quantizer known as distortion. Okay, it's very similar to the noise itself, but we will try to formulate in a different angle. Okay, so depending on the measure of distortion employed, there are two flavors of this distortion. Okay, we can define an average distortion, and there is something known as mean square distortion. Okay, so we'll try to understand these two types of distortion. Okay, one is average distortion, and another which is widely used in practice and which is a popular measure of distortion as well, which is called as squared error distortion. Okay, and if you try to minimize this, it's called as minimum mean square error of, you can say, MMSE kind of algorithm that you might have studied in your other courses, right? So we'll try to understand these two. Basically, this squared error distortion mathematically can be defined as X, which is the input message signal which is coming into the quantizer, difference between the input and the output, which is the error that we have defined as quantization error, and whose square is simply the squared error distortion. Okay, this mathematically can be denoted simply like this, and we know that this X cap is nothing but the quantizer output, the function of Q of X. Okay, and if you are using the squared error distortion measure, then the distortion is represented as, which is a function of X input and X hat, which is output. The distortion between these two, input and output, can be written as X minus X hat, which is nothing but Q of X, which is the function of the quantizer whole square. Okay, so in shorthand notation, sometimes this is denoted as X tilde square as well. So this represents the X tilde square represents the distortion used with the squared error kind of method of evaluating the performance of the quantizer. Okay, so in general, I can write this as the distortion D. Okay, so the distortion D in general can be written as, it is simply the expectation. This is the mean squared error distortion. So this is the mean value of this, which uses the expectation operator, expectation of D of X comma X hat, where capital X represents the random variable involved in input and output. Okay, which is nothing but expectation of X minus Q of X whole square. Okay, so this is the mean value or mean squared error distortion value. Okay, so this is nothing but mean square error. Okay, MSE in short form. We'll try to solve one of the numerical problems related to evaluation of distortion in our straightforward uniform quantizer. So in case of uniform quantizer, where we divided the continuous range of values equally, where the step size was constant across the division from say what I mean by that is, say if this is the minimum value of the message signal. Okay, so let us say this is the minimum value of the message signal. Try to draw this in with respect to the mid rise that we have taken in the earlier discussion. In case of uniform quantizer, okay, this will be clear when I try to apply onto certain specific values. Okay, so in case of mid rise quantizer, we know that this can be written as, for the mid rise, at the middle part that will be rising. Okay, and if I divide with equal partition of the cells and so on, and on the left hand side as well with a uniform division for the mid rise, this will be can be regarded as unit. Okay, I'll take 1 unit, that's not a problem, and this will go on for various levels and so on. And on the negative scale as well, this is the input output relation between the relation between input and output for the quantizer. Okay, so I'll give certain specific values to these. Say I have started from a level, say if this is an input, say if this is input and if this is output. So I'll start with an input level of A1, and if I go up to, say I'll take 8 levels of quantization, if that is the case. For an example, say if this is A1, A2, A3 and A4. Sorry, the center point would be A4 itself. This is the origin. This is A5, A6 and A7. If I take 8 levels of quantization, okay, so this where I've assumed mid-rise quantizer, okay, with number of levels in the quantization is 8. If that is the case, then the output which I can represent the output as, say if I start from this level, say for A1 this is the level, for A2 this is a level, and A3 and so on. This I can represent, say for A1, okay, I'll take this level, this as say x1 hat, this is the output, and I'll take this as x2 hat, x3 hat, and this center will be x4. Okay, this will be x4 hat, and this is x5 hat, x hat, 7, and finally for A7 this will be the point x8 cap. If this is the case with uniform quantizer for mid-rise type, and if I assume particular case for all these, okay, this will be interesting, where if I assume a source hex of t, okay, which is information signal, which is a stationary Gaussian source, Okay, say it is given as mean is 0. Let's assume that the Gaussian information source having mean 0 and having PSD, the power spectral density, as Sx of f, okay, as 2 between minus 1000 to, sorry, minus 100 to plus 100 hertz, and 0 say otherwise. Okay, and the source, the information signal is sampled, let's assume that at the exact at Nyquist rate, and each sample is quantized using this mid-rise quantization technique. Okay, so let's assume that there are certain levels for all these A1 to A7. So let's assume that, okay, I'll write here. So let's assume that say A1 is say around minus 60 and A2 is minus 40. Okay, A3 is minus 20, and so on, with a step size of 20. Say A5 is 20 and A6 is say 40 and A7 is plus 60. Extremes are plus and minus 60s, and accordingly, say let us, we have chosen the outputs x1 hat, say from x1 to x7 on the vertical line, sorry, x1 to x8 on the vertical line. X1 hat is, say, let us say minus 70. X2 hat is, let's assume that this is a uniform quantization. So uniformly we have to map from input to output. Okay, and so on. Okay, x4 would be how much? Minus 10. X5 will be how much? Plus 10. Okay, so I can write below here. Okay, X, I can say, I can start from X8, which is potentially plus 70. X7 would be plus 50, and X6 would be plus 30, and X5, okay, will be plus 10. Okay, basically the input output relation is linear, and hence it is uniform quantization. Say x1 being minus 70 be to x8 to be plus 70, and a1 is varying from minus 60 to plus 60. Okay, so this is how I have defined my quantization technique, and I have given an input information source which is a stationary Gaussian random process with mean 0 and having perspective density of this. So if it is given to you, if you are asked to calculate the distortion involved in this process, okay, our job is to find out with the mapping from input to output with the quantization process. It's a rounding off process, as I told. Say a range of input values is mapped to one quantum or one value at the output of quantization, where the input is the range of input. Say if this is xi, okay, all these values of input will be mapped onto one singular value, which is the output of the quantizer. We call that as xi hat. Okay, in mapping all these continuous ranges of values to one point, we are discretizing in the amplitude level as well, but at the cost of distortion. We'll be converting this continuous signal, analog signal, into a discrete amplitude signal. Okay, so we need to calculate the amount of distortion or amount of the cost that is incurred in losing out certain information in the original signal. So if you are asked to calculate the distortion, we can calculate with this sense, as we have defined the distortion mathematically as it's a mean squared value. This is a usual the mathematical relation that will be utilized to evaluate the performance of this quantizer, which is x minus x hat the whole square. Okay, which mathematically is defined as minus infinity to infinity x, where x hat is output of the quantizer times the power spectral density fx of sorry the PDF with a probability density function fx of x dx. Okay, so we know that the ranges of values is basically from 1 to 8. We have to consider a1 to 8 as the input levels of the information signal. We have considered this is varying from, I'm sorry, I scrolled up a little more. Yeah, we have divided the input levels to A1 to A7, and the output of the quantizer is varying from X1 to X8 cap, and hence we can apply the limits of this integration to say this is basically I have to consider all x's. Say this is vary from xi is equal to 1 to 8 for all regions. Okay, for all the cells varying from 1 to 8 between x minus q of x the whole square fx of x dx. Okay, so I believe this is a straightforward. Stop me and ask any doubts if you have. Okay, or equivalently, we know that this entire region of at the output is divided into several chunks. Say these chunks I can say this is from minus infinity to the first region, and you can stop at the point A1. Say what I'm talking here is for all the regions from minus infinity to A1 is one region, and all the regions between these AIs, say A1 to A2, A2 to A3, and up to A7 to A6 to A7. Okay, all these are the intermediate regions. So I can split this entire input ranges of values to three regions. One is from minus infinity to A1, and another is from A1 to A7, and another is from A7 to infinity. Okay, if I divide the regions in such way, so I will have this minus infinity to A1, and I can apply this as x minus the output q of x is basically x1 hat. Say for the region up till A1, this is simply x minus x1 hat is the output that you are going to give, x square fx of x dx plus the second set of region which will run from 2 to 7, A2 to A7. Okay, and hence this is integral. I can give a subscript as ai minus 1, say 2 can be substituted here, and up to ai. So this is basically a1 to a2 will be the first integral. Next will be a2 to a3 and so on. I think there is a question in the chat box. I will look into it. X minus x I hat whole square fx of x dx, and finally the third region which is from a7 to infinity x minus x hat 8 whole square fx of x dx. Okay, yeah. The question here is, what will be the quantized value exactly at A0 or A1, lower bit or higher? Exactly, that's what is the distortion involved here. So the region in between, okay, to answer to Amrit's question, all right. So the region between, to be very specific to his question, exactly at A0 or A1, exactly at, it's not A0 anywhere. I think your question would be somewhere in this region from A3, between A3 to A5. Okay, so all these values between A3 to A5 all will be mapped based on the rounding off function. Say if A3 to, if there are values between A3 to A4, all this will be mapped onto X4 hat. If there are values of the input between A4 to A5, all those value will be mapped onto X5 hat. Okay, so this is kind of a rounding off function. Say you'll take the lowest closest integer value belonging to the output. I think that was if there was a question, I think that's the answer. Similarly with respect to other regions as well. Say all the values between A2 to A3, all these values will be mapped to X3 hat. The only ambiguity that will arise between A3 to A5, where it is evident from this input output relation itself, where the regions belonging to A3 to A4 at the output of the quantizer will be mapped onto X4 hat. Okay, so all the regions in very strict, or to be specific to this question, all the input level voltages, say from -20 to 0, A3 to A4, all will be mapped onto -10. Okay, so if it is -15 as well, the output singular value will be -10 itself, and hence there is an error. So that's what is the cost that is going to incur in the transition from incur due to this quantizing. Okay, I hope that was your doubt. If that's anything else, you can ask me orally. Okay. Okay, as I told, this fx of x is the probability density function. Okay, this is actually a Gaussian. Say this is Gaussian with zero mean, that is what is given, with certain variance. Okay, so we don't know what is the variance of it. We need to calculate, because we are not given the PDF. We have given its power spectral density as x of f. Okay, so we can calculate the variance with the basic mathematical relation that comes from your unit 1, where the variance is nothing but expectation of x minus mu whole square, where mu is 0 here. So this is simply expectation of x square itself, where this I can say, in other words, this is your autocorrelation function exactly at tau is equal to 0, which we know that this is simply the area under the curve of power spectral density Sx of f df. Okay, so since we are given the information of power spectral density, I can substitute that, but this has value only between -100 to +100 hertz, as it's given in the problem statement itself, which has only between -100 to 100 with an amplitude of 2. So this will be simply 2 df, and hence this is simply 400. Okay, so this implies the input Gaussian process has zero mean and a variance of 400. Okay, so with this idea, I can now write fx of x, since it's a Gaussian, this is root 2 pi sigma square, which is 400, expectation of x minus mu the whole square. Say x minus mu the whole square is mu 0, so I can say simply as x divided by x minus mu the whole square divided by 2 sigma square. So where again sigma square is 400 in our case, so 2 times of 400 is 800. So of course this is x square. Okay, this is how a probability density function will look like. Now our job is to find out a distortion by substituting this fx of x into individual integrals. Say since we have given the actual values of these a1s, x1s, I mean ai's and xi's, where ai all these input levels a1 to a7. Okay, since we are given with these values, we need to substitute those values and get the output or get the distortion value. Since we know that this will be integral, with a certain lower limit and lower bound and upper bound with an exponential term, we know that such kind of functions can be treated as a Q function. Okay, we know that Q of x is nothing but it is defined as 1 over 2 pi integral say minus infinity to x e power minus say some dummy variable, say minus t square dt. Okay, t square by 2 if I'm not wrong. Okay, so this is how your Q function is defined as. So all these are exponential terms, and I can substitute these exponential terms and I can convert them all into a Q function. As I told, you can either make use of MATLAB functions or you can a MATLAB tool, as Q function is one of the function which is readily available in the MATLAB, or you can utilize standard Q tables which are available online as well and substitute on these, and I'll just write the final answer because it will be just tedious if I try to find out individual values. But you can apply such, either of the methods, specify that using Q tables or Q function of MATLAB. We can find out this distortion D. This will come out to be exactly, since I've calculated this to save time, this will be around 33.38. Okay, this will be the output. But this just solving is not our purpose. Solving the problem is not our the complete agenda today, but our purpose is to improve this distortion so that there will be minimum amount of error or distortion occurs due to quantization process. Okay, we have considered uniform quantization, we have considered scalar uniform quantization with the equal distribution of, if there is a linear relation between input and output, which has resulted with a distortion amount of 33.38. Imagine what if we had if you have not used quantization itself. Say if we were to use 0 bit per source. Say in other words, if we use 0 bit per source output. Okay, so if you have not used quantization at all, we know that distortion is basically expectation of x minus mu the whole square. This is simply expectation of x square itself, which is nothing but sigma square itself, which you have calculated is 400. So with the quantization process, or we can say the distortion has, with the quantization scheme, we have which is actually the quantization scheme that we have used here in our case is 3 bits per source output. Okay, that's 8 level of quantization. So with the quantization scheme, we have reduced the amount of distortion from 400 to 33.38. Okay, so we have at the, if you want to look at the receiver part, we have reduced the amount of distortion which would have been corrupted due to the channel in the noise in the channel itself, but we have reduced to around 33.8. So it's around a reduction of a factor of around approximately 12. Okay, reduced by a factor of 12. Okay, but we can enhance this reduction of quantization with a more robust quantization schemes. Okay, so with with that idea behind our behind our back, I can define the uniform distribution, uniform quantization in general. With this numerical example, I can quote in general for any uniform quantization scheme where we have defined the step size to be uniform, which is nothing but the difference between two successive input levels. Okay, where I is varying between say 1 to say n minus 2, where I have considered this. If you say I is equal to n minus 2, this is the difference between a n plus 1 minus a suffix n. With that idea, we can define the distortion in general as all the regions from minus infinity to a1, x is the input, minus what is the error in the uniform quantization. We know that error in the uniform quantization is plus or minus delta by 2. Okay, so the output will be either a1 plus delta by 2 or it is a1 minus delta by 2. Okay, that's is the amount of error. I'm sorry, that is the output of the quantizer. In other words, I can say x hat minus A is nothing but delta by 2 in the uniform quantization process. In other words, this hex hat I can say this is, sorry, this is plus or minus delta by 2. I can say hex hat would be the difference of the input level with the step size delta by 2. In general, I can remove this a, suffix 1, so that x minus x hat, which is the output of the quantizer, will be difference of the output minus the quantization error whole square times fx of x dx as the first region. As the intermediate regions, we'll have all the quantized output summing from 1 to n minus 2 integral. So in general, I can say this as I1 plus say I minus delta, and to A1 plus say I plus delta x. If you substitute actual values, whatever you have done in the previous problem, I'm just writing in general, nothing great in that. I'm just using generalized expression here, delta by 2 the whole square fx of x dx are the intermediate regions, and finally the final region is from A1 plus n minus 2 delta, the last point in the of the input scale. From that point to infinity, all the points from that point, in general A1. You need not remember, but if you have an idea to calculate the distortion for any given set of input and output, that should be more than enough. Fx of x or dx. Okay. All right. So this is in general with respect to uniform quantization, but this will not be enough in most of the cases. As you know, our say for example our speech signal itself, although our speech signal or the voice signal ranges from say a few hundreds of hertz to several values of kilohertz, all the frequencies will not be perceivable to all the frequencies will not have equal number of amplitudes. Or other words, you can say if you store a music, say a music video of say of 3 minutes of duration, the frequencies are not uniformly distributed over all the amplitudes. So in practical and in reality, you cannot use uniform quantization, where you will incur more amount of distortion for higher frequency ranges, where you will still have uniform quantization levels for higher frequency ranges, but you may not find most number of amplitudes which will appear in those frequency ranges. In such scenarios, you will have to move for an adaptive quantization process, or you can say a non-uniform quantization scheme. Okay, so with that, we will try to understand what amount of distortion that will be incurred in our case. Okay, we'll try to address such. Okay, so if you relax the condition that the quantization regions, say for except for the first one and the last one, be of equal length, that's what was with respect to uniform quantization, then we can minimize the distortion with less constraints. So that will result in a quantizer which will definitely perform much better than the uniform quantizer with the same number of levels. Okay, we are not going to compromise anything in the amount of number of representation levels. We are going to use same amount of representation levels, but the step size or the step length will not be uniform, be distributed across all ranges of input values. Okay, so let's assume that we are interested in designing the optimal mean squared error quantizer. So this is with respect to, I can give a particular heading to this, say optimal mean squared error quantizer. This is, in short, it is called as optimal quantizer. If that is the case, say let's say there are n quantization levels. Okay, I can define. There is no other constraint. Remember, I have just fixed, or I have just taken the same amount of representation levels as it is in uniform quantization. I'll not give any other constraints for non-uniform quantization. Only our job is to minimize the mean squared error distortion, okay, which you have calculated in the previous case, which will give us an optimum solution to this problem. So which in general, I'll write the distortion in such case. Definitely there will be certain minimum A1, and there is definitely there is a maximum. Okay, so this will vary from A1, A2 up to say AN minus 1. Okay, so a minimum amount of input voltage, input signal level is A1, and maximum is AN minus 1. So definitely again I can divide these regions into three parts. So one is from minus infinity to A1, which is x minus x1 hat whole square fx of dx plus similar analysis I1 to n minus 2 ai to ai plus 1 x minus x hat say I plus 1 whole square fx of x dx, and finally the last region, which is varying from I an minus 1 to infinity x minus x hat n whole square fx of x dx. Okay, so if this is the distortion which we want to minimize, as you can see here, how many number of variables that exist, because we have not fixed any regions here. I have not given specific step size to for the quantization process. So all these are variables themselves. Each of those xi's are variables. Each of these ai's are also variables. Right. So anyway, these AIs are variables, but I have not defined the boundaries for the quantization process. So I can say all these xi's are variables, in other words, and all these AIs are also variables. So how many xi's are there? Then it can be easily seen that there are n variables for the quantized output, or sorry, for the x variables, and there are this is output, and if this is an input. So there are n variables at the output and n minus 1 variables in the input, which is varying from a1 to an minus 1. So the totally 2n minus 1 variables in this expression. Okay, so in order to minimize, our job is to minimize the distortion. The distortion, whatever we have considered, is mean squared error itself. Okay, so we are going to minimize the mean squared error, which is your MMSE phenomena. Okay, so with that idea, what I need to do is to find out such values of AI and XI which will reduce, or which will give you minimum value of distortion. I need to do for all these 2n minus 1 variables. So I need to differentiate, I need to take the first order differentiation of this distortion function for all 2n minus 1 variables. Okay, so that would be one of the tedious steps. But if you take a particular case, let us take differentiating. Okay, don't go anywhere, because although it looks mathematically intensive, but it is not so. We'll apply this technique to the problem that we have solved just now for the non-uniform quantization, and we'll see how much amount of distortion again gets reduced by this process. Okay, so differentiating this with respect to, say, a particular variable AI, this will yield, since there are multiple variables, so this will be a partial derivative with respect to AI. Okay, this will give us, as you can see, for a particular variable AI. Okay, so all other integrals definitely can be taken, can be considered to be constant, and differentiation of such would be will be can uh, 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 be equated to 0. So with that, what will be left with is fx of x, which is small x is the input. Say I am taking a particular input which is AI. Okay, since after the integration will be applying upper limit and the lower limits, and differences of them would be the product, the second product term here, so which is nothing but AI minus xi hat whole square minus AI for the particular input. Say if I take this region x minus xi plus 1 hat, x is AI now, so the integration would give me AI minus x hat AI minus, I mean with the application of the upper limit and lower limit, minus of xi plus 1. Okay, so this would be the differentiation with respect to a particular input AI. So in order to minimize this, I need to find out that value of AI with first order differentiation be equated to 0. So this will give me, by solving, by expanding these terminologies, I mean these terms inside the square bracket, this is obviously AI will be equal to half of xi hat plus xi hat I plus 1, because this a minus b square and a minus b square, ai squares will get cancelled with each other, and finally two ab terms will be left over, and xi difference between xi and xi plus 1 with the minus sign will give you the mean of these two values. Okay, so this will be the one of the variable that this will result is this nothing but what does this mean? That this result simply means that an optimal quantizer has the boundaries of the quantization regions at the midpoint of the quantized values. Okay, so boundaries, AIs are the boundaries of the regions of the input signal. So it means that all these boundaries of quantization regions are nothing but midpoint of two successive quantized values. Okay, this is one of the important outcome of this one of the differentiation with respect to AI. We can again differentiate with respect to xi to determine the quantized value of the output of quantization process. So we need to differentiate. Of course, this is differentiation of d with respect to AI. Similarly, we can differentiate with respect to xi hat, which is another variable in the expression. Okay, let's define let's say a naught as minus infinity and say an as plus infinity. Say I'll take the entire ranges of the continuous values from minus infinity to plus infinity. Then I can write the first order differentiation of this with respect to xi. As you can see, this is between ai minus 1 and ai. As you can check back the integral here, the differentiation now with respect to xi, the quantity x cap, which is inside the integral, I mean which is inside the integral and which is squared. And if you take differentiation of that, say x minus the variable square, it will be simply twice of this variable itself into the PDF fx of x dx. Okay, so with that idea. So the differentiation with respect to xi will give twice of x minus xi hat times fx of x dx, which needs to be equated to 0 to find out the minimum, to find out the value of xi hat, for which we'll get the distortion minimum. This will result in xi hat by rearrange the terms. This will result in one of the important relation, integration ai minus 1 to ai. Since I can split this integral into two parts, which is one is x times fx of x dx, another is xi minus xi hat fx of x dx. So rearrange the term. This will give me x fx of x dx on the left hand side, which should be divided with respect to ai minus 1 ai fx of x dx. Okay, so this is basically arrived by this integral. This can be just going one step before. I have written this expression based on the rearrangement of these terms. Another integral term, moving this on to the right hand side, this will become positive. So this is nothing but xi hat fx of x dx. So xi hat, which is to be determined, which I have pulled out from the integral and rearrange the term, will give me this particular expression for the variable xi hat. Okay, so this relation is known as, okay, whatever the expression this shows for the optimal quantizer, this is the quantized value for a region which is given by this, is known as Lloyd Max condition. It's named after two scientists, Lloyd and Max, and hence it is known as Lloyd Max condition for quantized value of optimum quantizer. Okay, so in other words, we can say this is nothing but, in other words, this is actually the representation point or the quantized value. It should be chosen in a such that this should be centroid of the region. Okay, since it's a non-uniform distribution of non-uniform quantized outputs with respect to the ranges of inputs from ai minus 1 to ai, and hence, in other words, this is not the mean or the center point. This is nothing but the centroid of the region in a mathematical term. The usual process, or the two conditions that we have defined with this process, can be summarized in this way. Okay, this is what is required for us to take it further. Okay, so whatever you have discussed can be summarized for the criteria for optimal quantization as the first condition, or the first criteria is boundary of the quantization regions, as I had stated earlier with ai. The value that you have got, the differentiation with respect to ai, which says that boundary of the quantization regions are the midpoints. Okay, are the midpoints of corresponding quantized values. And the second condition that, or the second criteria that we have obtained from the Lloyd Max condition, is that the quantized values quantized values are the centroids of the quantization regions. Okay, so although these rules are appear to be very simple by the statement, but they do not result in an analytical solutions to these optimal quantizer design. The usual practical method of designing the optimal quantizer is to say start with the quantization regions, say with a set of quantization regions. You begin the quantization process, and then using the second criteria, using the Lloyd Max criteria, then you can find out the quantized values. Then we design a new quantization region from this point for a new quantized from after obtaining the quantization regions. Again we can define the quantized values. So this step 2 and step 1 will be iterative kind of operation, which will be considered as an algorithmic process or numerical computation process, which will run for several iterations, and after some certain iterations you will obtain a constant distortion level. Then we can stop the algorithm and we can say this is a minimum amount of distortion that is possible for certain mapping from input to output for the analog to digital conversion. Okay, so in other words, I can say just start with the random quantization regions and get the quantized values. Then again do the process again with the step 1 and do this iteration for several values. Okay, so this is actually the method which is used in practical scenarios for various source statistics, irrespective of the source statistics. Since here we have taken zero mean, since we have taken here Gaussian with mean 0 and variance sigma square, this can be extended to non-zero means and non-unit variance processes as well. Okay, so if that is the case, if it's a non-mean, then all these AI values for non-mean input random process, all you need to replace this AI with with an addition of mean m. Okay, with an addition of mean m, which will result as with mean m and a standard deviation of sigma times ai, and all these xi hat can be replaced with the mean, the actual mean, and sigma xi hat. Okay, so these are the are the cases with in general for a Gaussian source with mean m and variance sigma square. There is actually a standard set of table itself is available for the designer. So this is one of the standard set of table which is available the designer, where this is particularly for mean 0 and unit variance. Okay, say if I have chosen capital N is equal to 8, say I have chosen in our case. So if I go back to an example that we have considered here. Okay, so I'll try to solve for the optimal quantizer. Okay, so this was the example that I had taken. Okay, so this with mean 0 and certain variance as sigma square as 400. I think that's what we had got in this question. Sigma square was 400, right? So there is a standard table given in order to calculate the amount of distortion that incurs from the quantization process. So if you take the same example, it is given that this table is actually specifically for a Gaussian process for mean 0 and sigma square is equal to 1. But in our example, we have got mean 0 is fine. We have got mean as 0, but sigma square as 400. So we have to replace this, and number of quantizers levels is n is equal to 8. So with this only information of the design, we can find out, or we can divide the regions of inputs with a non-uniform quantization, and we can accordingly find out the output of the quantization process as well. So with the help of this standard table, since n is equal to 8 is given, so we need to consider this particular values of ai, and these set of values for xi, and this is the amount of distortion that will be resulting in such Gaussian source with mean 0 and sigma square 1. All we need to do is, for non unit variance Gaussian source, we need to replace all these AIs, as I told. All these AIs you replace with m plus sigma times AI, and all these xi hats replace with m plus sigma xi hat, and finally you replace d with sigma square di for that particular case. Okay, I mean there is no di, I mean just distortion d. Okay, so what will be my quantization levels? It is given as plus or minus ai. What we have with us is a1 to a6, if I'm not wrong. I'll just take that question again, try to solve for optimal quantization. Say here a1 is varying from minus 60 to plus 60. I mean a is varying from minus 60 to plus 60. So a1 and a7 are plus or minus 60s, or plus or minus 40, or plus or minus 20, and a4 being 0. And similarly for x is varying with respect to in that value. So all I need to say is all these a1 and a7. Okay, so a1 will be replaced with m is 0, sigma is 20, the square root of 400 is 20. So this will be 20 times, how much is that? 0.5006. 0.5006. For a7 this is minus 20, 0.5006, and whatever value that you get. And similarly for a2 and a6, you can say what was a2 there? Just go back. a2 is minus 40. Say a2 is, okay, this should have been minus and this should have been plus. So this is minus 40. And what is another quantization level that is given to us? 1.050. So this a6 is plus 40 into 1.050. And finally a3 and a7. a3 is given as, with the actual value of this is plus and minus 20, a3 and a5s. So this is a3 and a5. This is minus 20 into another set of value, which is 1.748, and this is plus 20 into 1.748. So you can calculate the region boundaries with all these values of AIs. And of course a4 is a 0. So another quantization level here, it is, I mean boundary region is a4 itself is 0. Similarly you can find out the outputs x1 and x, I mean there are 8 sets of values, and hence there are 4 values for plus and minus, x1 and x8, x2 and x7, and so on. So we can accordingly multiply with plus sign and minus sign to find out the quantized output. And finally the distortion d is sigma square times, I mean d dash if I say, which is 0.03454. I do the calculation, and this will give me around, say around 13.816. Okay, so what was the distortion with respect to uniform quantization? We had calculated this earlier. With uniform quantization, the distortion was coming out to be around 33.38. The new quantized, I mean new with a non-uniform quantization using Lloyd-Max quantizer algorithm, we will get d dash as around 13.82. See the difference, or the scaled down version of distortion from with a factor of I can say with a factor of around you know 2 itself, the distortion gets reduced. Okay, you can calculate with respect to the variations of distortion from uniform to non-uniform quantization using a decibel value as well. Okay, I think it's kind of a little intensive with respect to mathematical relations, but all you need to know is the final outcome or the final algorithm which is involved in obtaining the criteria for optimal quantization.